Hello everyone and welcome to this presentation. My name is Sabah Hejazisani and today I will be presenting our research project titled Simulation, Performance Evaluation and Robustness Analysis of Fuzzy Adaptive Cruise Control with the Model Predictive Control. This research was conducted at KN2C University of Technology under the supervision of Dr. Saeed Khankalantay. Let's dive into the details. To begin with the context, autonomous vehicles and advanced driver assistance systems rely heavily on adaptive cruise control for longitudinal navigation. Unlike conventional cruise control that only keeps a fixed speed, ACC uses forward-looking sensors such as radar or LiDAR to measure distance and relative velocity to the lead vehicle in real time, automatically regulating vehicle speed in dynamic traffic. Designing an effective ACC system is challenging because it involves three conflicting goals. First, safety, ensuring absolute collision avoidance by maintaining a safe following distance. Second, passenger comfort, which means minimizing jerk and sudden changes in acceleration. And third, fuel economy, which requires eliminating aggressive throttle and braking cycles. Balancing these competing objectives in the core problem we addresses. Traditional model predictive control approach typically use constant weighting parameters in their cost function. Because these weights are fixed, the controller cannot dynamically adapt to sudden traffic cuts or emergency braking. This leads to either overly aggressive or overly sluggish behavior. Furthermore, some literature proposes dual controllers, one for tracking and one for energy management, which introduces significant computational overhead on vehicle ECUs. To overcome these limitations, we implemented the unified AFAC-MPC architecture. This approach combines model predictive control with fuzzy logic in a single unified layer. The fuzzy engine evaluates driving states in real time and dynamically tunes the MPC cost weights. As well, we see this single controller achieves optimal multi-objective balance and robust performance under disturbance. Moving to the mathematical modeling, the lower-level vehicle dynamics and actuator lag are modeled as a first-order low-pass filter with a time constant 0.5 seconds. Discretizing this model with a sample time of 0.1 seconds give us the discrete acceleration update rule shown here. This accurately captures actuator delays and ensures that control commands remain physically realistic. The dynamic safe following distance is defined based on a fixed standstill gap of 10 meters, plus a speed-dependent headway with a time gap of 1.5 seconds. Our state vector consists of two primary error states, delta D, the spacing error, and delta V, the relative velocity between the lead and ego vehicle. The discrete state space formulation maps these errors directly into the controller. At each time step, the MPC solves an online constraint optimization problem over a prediction horizon. The cost function penalizes spacing error with the weight alpha 1, velocity error with alpha 2, and control error with weight beta. We enforce hard physical constraints on non-negative spacing error to prevent collisions, as well as strict bounds on velocity, acceleration, and actuator inputs. Instead of one complex MIMO fuzzy block, the system employs three separate multi-input single-output Mamdani fuzzy systems. FLS1 generates alpha 1 for distance safety, FLS2 generates alpha 2 for velocity tracking, and FLS3 computes beta for control, effort, and comfort. Each system takes the same three real-time inputs: spacing error, relative velocity, and ego acceleration. To ensure fast real-time execution within our 0.1 second sampling period, triangular and trapezoidal membership functions are used. Linguistic terms are divided into low negative, medium 0, and high positive. We apply the center of gravity defuzzification method, which provides smooth deterministic weight outputs with very low computational burden. The rule base consists of 27 fuzzy rules designed around 3 key operating modes. In safety priority mode, when spacing error is low, alpha 1 is driven to high, making collision avoidance the top priority. In speed tracking mode, when the gap is safe, alpha 2 becomes high to match the lead vehicle smoothly. And in eco and comfort mode, during steady state cruising, beta is increased to eliminate actuator chattering and save fuel. Here we see the overall closed-loop architecture in Simulink. Radar or LiDAR measures the lead vehicle motion and extracts dynamics error. The fuzzy logic system continuously updates the weighting parameters alpha 1, alpha 2, and beta. These weights feed into the MPC solver, which generates the optimal acceleration command executed by the ego vehicle dynamics. We evaluated the system across 2 standard driving cycles. First, the HWFET cycle, representing highway driving over 16.5 km for 765 seconds with high speeds and gentle transitions. Second, the FTP75 cycle, representing urban driving over 17.77 km for 1,777 seconds with frequent stop-and-go patterns and rapid speed variations. Starting with the HWFET highway results. The ego vehicle starts with an initial distance of 200 meters. FACMPC smoothly closes the gap and converts to the safe distance line without any dangerous undershoot. Notice how velocity tracking matches the lead vehicle accurately, avoiding the large initial speed overshoot that occurs in the fixed weight baseline. Looking at acceleration and jerk profiles in the highway cycle, the fixed weight controller suffers from high-frequency actuator chattering, especially during initial transient and braking phases. In contrast, FACMPC provides a clean, continuous acceleration profile, achieving a remarkable 63.2% reduction in average jerk, significantly enhancing passenger comfort. In the urban FTP75 cycle, the challenges are much higher due to repeated stop-and-go maneuvers. FACMPC tightly tracks the safe distance reference throughout all traffic stops. The baseline ACC creates excessive gap spikes of up to 80 meters, which weights road capacity, whereas our fuzzy adaptive controller maintains tight, safe following. Examining the acceleration and jerk in the urban cycle, the benefits of fuzzy weight adaptation become even more pronounced. While the fixed weight system shows severe chattering and heavy vibration bands, FACMPC eliminates these oscillations entirely, achieving a 76.3% reduction in average jerk across the entire 1,877 seconds. To summarize our nominal simulation results quantitatively, on the highway cycle, FACMPC achieved a 63.2% reduction in jerk and a 30.2% improvement in distance tracking RMSE. On the urban cycle, it delivered a 76.3% jerk reduction, a 26.4% improvement in distance RMSE, and a 16.6% lower average acceleration, directly translating to lower energy consumption. Minor visual differences in a raw plot spikes compared to the paper arise from undisclosed proprietary solver setting, but the quantitative trends fully match. To validate the practical reliability of FACMPC, we tested 3 challenging disturbance scenarios. Scenario Alpha, high-frequency band-limited radar sensor noise. Scenario Beta, complete temporary sensor communication blackout for 10 seconds. And Scenario Gamma, parametric uncertainties evaluated via 100 stochastic Monte Carlo runs. In Scenario Alpha, band-limited white noise with a noise power of 0.3 is injected into the lead velocity signal between t equal 250 and 260 seconds. The noise is modeled using the power spectral density equation shown on this slide, with a cutoff frequency around 1.59 Hz and a Nyquist frequency of 5 Hz, simulating real-world sensor inaccuracies. Here are the simulation results under scenario alpha for both driving cycles. Despite the lead velocity telemetry experiencing extreme high-frequency fluctuations between 15 and 28 meters per second, the ego vehicle velocity remains completely smooth. The fuzzy engine instantly increases the control effort weight beta, actively filtering high-frequency noise from reaching the throttle, and brakes while keeping distance deviation below 1.5 meter. Scenario beta tests fail-safe behavior. Between 280 and 290 seconds, the lead vehicle velocity signal drops to zero, simulating sensor blackout. As seen in the diagram, the controller immediately engaged defensive deceleration, reducing speed safely from 22 to 10 meters per second, expanding the safety gap up to 180 meters to guarantee collision avoidance. Once communication is restored at t equal to 290 seconds, the fuzzy engine detects the enlarged gap and dynamically boosts the velocity tracking weight alpha 2. As shown across both HWFET and FTP75 cycle, the ego vehicle accelerates smoothly and reconverts to nominal cruising speed and safe distance in less than 20 seconds, completely without overshoot or instability. In scenario gamma, we evaluated environmental sensitivity using 100 stochastic Monte Carlo simulation runs. We introduced random plus or minus 5% variation across 4 key parameters: wind direction, wind speed, rolling resistance coefficient, and road slope. This assesses how fuel economy holds up under unpredictable driving conditions. The resulting box plots clearly show the economic advantage of FACMPC across all 4 parameters. For wind direction, wind speed, rolling resistance, and road grade, FACMPC consistently maintains a lower median fuel consumption and significantly narrower interstructural range compared to the baseline ACC. The tighter whiskers prove that the fuzzy adaptive weighting prevents unnecessary throttle compensation. Quantifying the overall economic robustness under environmental uncertainty, FACMPC fuel consumption increased from 7.858 to 8.110 liters per 100 kilometer, which is only a 3.21% increases. In contrast, the conventional ACC saw the fuel consumption rise by 7.03%. This confirms that FACMPC provides more than twice the economic robustness against real-world disturbances. To summarize the core achievements of this work, first, we successfully unified multi-objective tracking into a single-layer fuzzy MPC framework. Second, we achieved superior passenger comfort with up to 76.3% jerk reduction while strictly guaranteeing safety. And third, we verified comprehensive fault tolerance against noise sensor dropouts and environmental uncertainties. Before real-world deployment, several practical challenges must be considered. Solving quadratic. Programming online requires efficient embedded solvers for automotive ECUs. We also need to account for hardware limitations such as sensor calibration, drift, actuator wear, and edge case tuning in severe weather conditions, like heavy rain or snow. As promising future research directions, first, integrating human-in-the-loop control, where the driver's cognitive load is monitored via facial analysis and eye tracking to adaptively adjust safety weights. Second, deploying code on microcontrollers for hardware-in-the-loop testing. Third, extending FACMPC to 2D combined longitudinal and lateral steering control. And finally, studying string stability in connected autonomous vehicle platforms with V2V network delays. This concludes the presentation of our fuzzy adaptive cruise control with MPC project validated against state-of-the-art literature published in engineering applications of artificial intelligence. Thank you very much for your time and attention, and I will be happy to take any questions.